All right, the fact that the moon is tilted with respect to the ecliptic and not, it's closer to the ecliptic, which remember is that's the plane of the solar system. That's where the sun is. Um, Tells us something about the moon, right? It actually tells us something about the origin of the moon. The fact that it lines up closer to the ecliptic than than it does the Earth's equator says that the moon was not originally formed with the Earth, right? So if you look at the moons around other planets in our solar system, they line up with the equator of their host planets. Like Saturn's moons, for example, line up very nicely. Saturn's tilted actually a little bit more than Earth, and the moons line up, and Jupiter, which is not tilted that much, it is a little bit tilted. The moons line up with the equator of the host planet. In other words, that's a pretty standard thing. And when they don't line up with the equator of the host planet, that tells you that the moon had some different type of origin, that it didn't necessarily start or did not start at the same time that the planet that its host planet did. Um, all right, so that guy, we're leading to the origins of the moon. Notice this is the let's see this is showing us elevation. Notice the elevation on the far side of the moon is much higher. There are less. So these are the two main Maria. Uh, it's much higher in elevation there than even the highlands on the moon, on the near side of the moon. All right, let's see. All right, so now going back before the astronauts visited the moon and brought back rocks, there were several competing theories, and let's look at those. Let's look at the three theories. These are the three major theories that were being played with in the not played with, but were being considered, if you will, in the 1950s. One was the capture theory, right? So maybe a small planet. There was a planet that was orbiting the sun, and the Earth's gravity, it got too close and it was captured. All right. So if that's the case, then when we look at the rocks on the moon and the rocks on the Earth, they should be completely different. Like for example, the rocks on Earth and the rocks on Mars are very different from each other. You can tell that that they're not the same. It's not the same planet. All right. The Earth and the Moon are twins formed side by side. This is called the twin formation theory. That the same cloud of material that made the Earth also made the Moon. That's so that they would be identical. And then there's this other one called the fission theory, that the Moon spun out very fast from a rotating Earth in the early days of the solar system. All right. So again, the results of each of these would it tells us something about the makeup of the rocks on the moon. All right. So each of these hypotheses gives a different prediction to the moon's composition. If the capture theory, the moon would be very different, right? Because it was formed somewhere else, the way Mars is different from the Earth. The twin theory would require that they have the exact same composition. The fission theory, the moon's composition should be pretty much the same as the Earth's crust. All right. And then moon rocks were brought back in the 1960s. For some elements, some of the elements on the periodic table, the composition was exactly the same. But for others, it was very, very different. All right. So none of these three hypotheses that we had, the capture theory, the twin formation, and the fission theory, worked. right? This is a beautiful example of science, at its core, right? You have these ideas, and then you have experimental evidence, bringing the moon rocks back, analyzing their composition, and you find that none of them are right, right? And so there was actually in the 1960s there was another theory that was proposed, and at first people ignored it. They thought it was nonsense. But when the moon rocks came back, it seemed to be that they were onto something. The people who were backing this, it's called the large impact hypothesis. All right, so here's the basic idea. There was a large object in the early solar system, something about the size of Mars. In fact, in astronomy, we love to name stuff. It's a pretty standard thing to do. And so this small body, roughly 4 billion years ago, that crashed into the Earth at a glancing angle, as you can see there, it didn't hit head on. It hit at a glancing angle. It's actually has the name Theia. I don't know who named it that, but that this name has stuck. And so Theia, this Mars-sized object, hit the Earth, and of course Theia doesn't exist anymore. It's now part of it is scattered all over the surface of the Earth, and some of it sunk down into the Earth, and then the rest of it becomes so after let me go through this. After the collision, the Theia and the Earth turned molten. Some of the rocky material ended up in orbit around the Earth and coalesced, that is, gravitationally assembled itself into a sphere, and that sphere cooled off, and that's what we call the moon. And notice, of course, remember, it's not, the moon does not orbit the Earth along the Earth's axis or along the Earth's tilt. Right, it's closer to the ecliptic. In fact, it's only 5 degrees from the ecliptic, which tells us that this was a planet that was orbiting the sun. It got too close and actually struck the Earth. Lots of things hit the Earth, but this impact was big enough to cause the moon to form. All right, and so that's the age of the lunar rocks, and the lack of an impact site on Earth suggests that this occurred, not quite 4.5 billion years ago, but more than 4 billion years ago. All right. So this idea, the impact would have vaporized its low melting point, the water, for example, dispersed, explained the lack of any water on the moon. That's another thing. Okay, so when the astronauts brought back the rocks from the moon, so look at this picture. Remember, if this was a Mars-sized object, it probably had a good amount of water on it, and so when this thing hit the Earth, that those water molecules are still going to, they actually become part of the Earth. But then, this fiery ball that's in orbit around the Earth that eventually gravitationally coalesces into the moon, is extremely dry. Like we were actually really surprised when we analyzed the moon rocks at how dry they were. They're almost completely lacking in any water. Which actually goes exactly along with the large impact theory. It exactly is what you would expect. All right. So and the fact that some of the elements are the same and some of them are very different means that this, oops, I missed the picture. That Theia came into contact with the Earth, but only for a really short time. Exchanging materials, only some of the materials. All right, so and then also the fact that it doesn't follow the Earth's equator. Let's keep going here. All right, so now we're going to talk about the tides. I'll see if I can get through this entire thing. So the moon is primarily responsible for the tides, and it has to do with what's called differential gravitation. Right, so the moon basically pulls on one side of the Earth stronger than the side that is like at 90 degrees to the Earth, 90 degrees to the moon, at an angle of 90 degrees. So this side, the side that faces the moon, the water piles up, all right, and that's in fact a high tide. And the thing that I have to explain is, what about this high tide over here on the opposite side of the Earth? Right? Why is this piling up? And it has to do with inertia, right? For example, if you might have done this as a kid or something. If you take a bucket and you got some water in the bucket, you flip it upside down, the water's going to come out, right? That's pretty obvious. But if you tied a rope to the handle of the bucket and you spun it around fast enough, you could actually spin the bucket upside down, right? And so the water will pile up, and the reason that it's doing that is because of what's called inertia, because it's moving fast enough, and it causes the water to pile up, and it piles up exactly opposite the direction of the moon. So it piles up. That this is a high tide, right? This is a low. Let's see, how do we have this? So we have it. So we're looking at the North Pole right here. So this is, as you're looking at the North Pole. So what happens is the water piles up over here. Remember, the Earth is rotating. Then so you pick a spot on the Earth, and then what's going to happen is it's in a high tide. As 6 hours later, you're in a low tide. 6 hours later, you're in a high tide again. 6 hours later, you're in a low tide. But and then of course 6 hours later. Actually, it's not exactly 6 hours later, because during that 24-hour period, the moon has actually moved by about 50 minutes, not quite an hour. So the moon is a little bit over. It's not where it was the day before. The moon is over here, and so the high tide is going to be like an hour later, or really 50 minutes later. If you ever, if you go to the ocean, and it's 9 o'clock in the morning, and it's a high tide, it's exactly high tide right at 9 o'clock in the morning. You get up, you wanted to go for a walk along the beach, along the shoreline, and you notice that the water's it's exactly a high tide at that moment. You get up the next day, and 50 minutes later, there's going to be a high tide. And then the day after that, it's 50 minutes later, right? Because the moon is moving around the Earth. And so the high tide follows them. It always follows the moon, right? And then, of course, 180 degrees on the other side, that's also a high tide, right? So we rotate into the high tide, we rotate out of the high tide. So this is, the tidal bulge comes from this differential gravitation. The moon also experiences tides, just to let you know, but it's made of solid material. So, the rock doesn't really pile up very much compared to what the water does on the Earth, right? The water really piles up, several meters in some places. All right, so here's a good example. Like, here's a house, during low tide. 6 hours later, it's in high tide. 6 hours later than that, it's in low tide again, and 6 hours, it's in high tide again. All right, so two high tides a day, 2 low tides a day, and each day they're offset by about 50 minutes. All right, so I'm gonna finish this up in the next, or try to finish this up in the next video.